Hey Ahmed, how are you?
Hi, fine. What about you?
Doing good too. What time is it for you over there right now? Okay. Uh, I see that you also wanted to go over stereoisomers. Are there any specific problems or questions that you had to start off with?
No, no, just Deco. Enough.
Okay, like we could start with RS configuration, right? So let's start off with identifying what a chiral center is, right? So a chiral center is going to be a carbon with four unique groups, right? So an example would be something like this, where a carbon will have four bonds to be neutral, and three-dimensionally, two of the bonds would be flat in the plane, which is drawn like those lines right there, and one bond would go towards the page, out of the page, towards you. The other bond is going to go into the page away from you, right? And we call this a wedge bond, which is going up out of the page towards you. And we call this a dash bond, which is going to be going away from you into the page, right? So let's say, for example, we have a hydrogen here, a bromine here, a methyl on this carbon, and then an ethyl on this carbon right here. Right. This is a chiral center because there are four unique groups attached to this carbon. There is a bromine group, there is a hydrogen group, there's a methyl group, and there is an ethyl group. Right. Now, when there's a chiral center, we now can assign R and S. So to assign R and S, there's three steps. You rank the groups, right, in terms of atomic number, right? Atomic number. Now, once you do that, you have to make sure that the lowest priority group is on the back, right? So the priority group number four, the lowest priority group has to be on the back. Lowest priority group on the back, right? So now once you've done that, the last step here is to trace the direction of the groups, right? If it is going clockwise, then it's going to be R. If it is going counterclockwise, it is going to be S. Right. So let's take a look at this chiral center here. We see that there are four groups attached to it, and the atom that you're looking at here is the very first atom attached to this carbon. We have a bromine, a hydrogen, a carbon, and a carbon. Bromine has the highest atomic number, so that is priority group number one. Hydrogen has the lowest atomic number, so that is going to be priority group number four. Now, there is a tie between this carbon and this carbon because they have the same atomic number. And if there's a tie, you look at what three other atoms is the atom attached to. So we see that this carbon over here on the left is attached to three hydrogens. One, two, three hydrogens. So we could write that out here, three hydrogens. Whereas this carbon right here is attached to one carbon and two hydrogens. One carbon and two hydrogens. So we now see that this carbon here has a higher atomic number than this hydrogen, making this carbon be priority group number two, and this carbon will be priority group number three, right? Now we see our one, two, three, four functional groups, and we see that the lowest priority group here, hydrogen, is on the backside, the dash, so that's good. Now we can rotate one, two, three, or trace the direction this way. which is going clockwise. And if it's going clockwise, that is going to be in R configuration right there, like that, right? Now, I'm going to give you an example of when the lowest priority group is not on the backside. For example, if we have something like this, right? Where we know that this carbon here, that is the red star, is a chiral center because there's four groups attached to it. This alcohol, this hydrogen, this methyl, and this ethyl here. So when we assign priority in terms of atomic number, this oxygen will be priority number 1, this hydrogen will be number 4, this would be number 2, this would be number 3, right? But now look at the lowest priority group hydrogen here. It's on the wedge going towards you. So we cannot do it normally, right? But a trick here is that you just trace it how it looks like, which is going to be clockwise R. It looks R, but it's not actually R. You invert it, right? So it's going to be S. And the reason why we do that is because the lowest priority group here, hydrogen, is on the wedge, right? Okay. Any questions on this so far?
So clear, thanks.
That's good. That's good. So now there is another tricky example where the lowest priority group is on the flat planar bond. So for example, if you have this chiral center here, right, where we see that the lowest priority group hydrogen over here is not on a wedge or a dash bond. So we cannot use that trick where we invert whatever it looks like. What we have to do is that we have to rotate this single bond right here, rotating these three groups around. And I'm gonna keep this group stationary still. So when I do that, I'm going to move the hydrogen to the backside. So I don't want to go to this direction because if I go that direction, the hydrogen is going to go on the wedge, but I want the hydrogen to be on the dash. So I'm going to go to this direction here. That would move the SH group to the wedge, and then the chlorine would be the flat planar bond. So when I redraw the structure over here, this would be chlorine. This would be the hydrogen, and the wedge would now be the SH. Right? So notice how the flat planar bond dash wedge stayed at the same positions. What changed was the groups attached to those bonds, right? So now this works out because our lowest priority group, hydrogen here, is on the backside, the dash, right? So if we look at this correspondence right here, this is going to be priority group number 1. This is going to be priority group number 2. This is going to be priority group number 3. This is priority group number 4. So when we trace the direction here, going this way is clockwise, so it is going to be R, like that. Okay. Now let's relate this back into stereoisomers, right? So stereo isomers are going to be,
Just a
well,
question.
yeah. Mhm.
The hydrogen is always the lowest group.
Yes, hydrogen will always be the lowest group. Correct.
Why?
Because hydrogen is going to have the lowest atomic number, right? If you look at the periodic table, hydrogen has an atomic number of 1, and when we assign the priority group, we look at the atomic number of each um, atom attached to the chiral center. Chlorine here has the highest atomic number on the periodic table, so that's why that's priority group number 1. Oh wait, let me double check this. Let me double check the periodic table with you really quick. Periodic table, right? Yeah. So if you look here on this periodic table, hydrogen has atomic number of 1
Yeah, yeah.
right here. And we see chlorine has atomic number of 17, sulfur has atomic number of 16, right? And then carbon has atomic number of 6. When we assign priority, that is going to be in terms of atomic number. So that's why chlorine is number 1 because it has atomic number 17. Sulfur has atomic number of 16. Carbon has atomic number of 6. And then hydrogen has the atomic number of 1, which is the lowest on the periodic table, right?
That's so clear.
Mm-hmm.
Thanks.
Yep. Yep. That's good. Okay. Now, if we take a look at the definition of isomers, isomers are going to have the same chemical formula, right? Um, and they're going to be different in terms of how they are spatially oriented, right? Spatial orientation. So where they are in space. And I'll show you an example of what I mean by that, right? So for example, if I have this molecule versus this molecule, right? 1, 2, 3, 4. That's C4. 1, 2, 3, 4, 5, 6, 7, 8, 9. H9, Br. Same thing as for this. This is C4, H9, Br, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. These two molecules here have the same chemical formula, C4H9Br, but they are stereoisomers of each other because they have different spatial orientation, right? They are different. And the reason why they're different is because if you take a look at this bromine here, this bromine is going out of the page towards you as a wedge bond. If you look at this bromine over here, this bromine with the dash is going into the page away from you. So this bromine here is farther away from you. This bromine here is closer to you. So that's why they have different spatial orientation. They have different things in space, right? But then they have the same chemical formula here, right? Now as practice here, can you tell me for this red chiral center here, what is the R and S configuration? Like, is it R or is it S? And let me know your thought process on how you do that.
That's enough.
R, yep, correct. So that is R, correct? Because it's 1, 2, 3. Hydrogen is 4, going clockwise, R. How about for the blue one here?
I think that's also an R.
So this is 1, 2, 3, going this way. It looks R, right? But look at the hydrogen here that is invisible, which has to be a wedge because this carbon here already has 2 flat bonds and a dash, right? This hydrogen here that has the lowest priority group is on a wedge. So we have to invert whatever it looks like. It looks like an R, but it is an S instead, right? Because if you look at the previous one over here, the hydrogen, the lowest priority group, is already on the backside, so we don't have to invert or flip anything. We could just do it like normally, which is R clockwise. That's good. But in this case here, we would have to flip it at the end. We would have to invert it at the end because the lowest priority group hydrogen is not on the dash on the back, like that, right?
That's,
Now, mhm. Any questions on that
uh,
one?
no, no, thanks.
Yeah, that's good. Now, you notice how we have these two car centers here? They have opposite stereochemistry. Like this car center here is R, and this car center here is S. If all chiral centers are inverted, then that means that those two molecules are going to be enantiomers of each other. right? So this molecule is an enantiomer of this molecule here, right? Now I'm gonna introduce you diastereomers as well. Diastereomers are gonna be when some chiral centers invert and some chiral centers
What's the meaning of antimer?
stay the same. Yep. So enantiomer are gonna be two molecules that are non-superimposable from each other. So think of it like your hands, right? Like you have a right hand and a left hand. Um, if you try stacking them on top of each other, like they will not match, right? They're non-superimposable from each other. They give it like the mirror image of something, right? So
Clear, clear.
yep, uh-huh, that's good. That's good. Now, enantiomers will have the same physical and chemical properties, but different optical activity. So what I mean by that is, this is gonna get more into like the properties of these, right? When we shine light through this molecule here, this color sensor can rotate that light to a certain degree. So let's say, just for an example, it rotates it because this is R, let's say positive 50 degrees clockwise, right? So then if this is the enantiomer of this, then if we shine light through this molecule, it's going to rotate this 50 degrees counterclockwise. So they rotate the light in the same magnitude, meaning the same number, right? But opposite direction, right? The direction. So enantiomers will have the same chemical and physical properties like melting point, boiling point, but they will have different optical activity. Okay. Whereas if you look at diastereomers over here, where some color centers invert and some color centers stay the same, they will have different physical properties. But let me look at the chemical properties. The do diastereomers have different chemical properties as well? Yes, chemical and physical properties. Right, they're not mirror images. They will have different chemical and physical properties. Okay, so I'll give you an example of two molecules that are going to be direct stemers from each other, right? So let's say, for example, we have this molecule and this molecule here. There are two color centers. There's this red color center and there's this blue color center. Same as for this molecule here, right? Without even assigning R and S, we know that this red color center will stay the same, right? It will not invert. But we look at the blue color center here, we see that that would invert, right? So let's just practice here. Um, can you tell me the RS configuration for the red color center on this molecule here on the left side?
The connection was good. Can you repeat for me?
Uh-huh. Yeah. So for this red color center here, what is the R and or S configuration? Like, is it R or is it S?
That's an R.
Mhm. R. So let's assign priority here. This is one. This is two. This is three. And if we go this way, that is going um counterclockwise, right? Which looks S, but let's make sure the hydrogen here, the hydrogen is on the back. So that is number four. So that's good. It will stay as an S. How did you get R? Like what priority? What groups did you assign like for priority? Like what's your priority group number one, two, and three here? Right, right.
Priority for to the hydrogen.
The hydrogen is priority group number no, oh,
No, bro.
number four, right? Because remember how we said earlier that hydrogen has the lowest atomic number on the periodic table, right? So that's why it's priority group number four. Um, Now there is a tie between all these carbons right here. But if you look at this carbon over here, this carbon is attached to one bromine, one carbon, and one hydrogen. This carbon over here is attached to two carbons and one hydrogen. This carbon over here is attached to one carbon and two hydrogens. So that's why this will be priority number one, this carbon will be priority number two, and this carbon will be priority group number three, like that. Whereas this hydrogen will be priority group number four, right? And then if we go this way, that's counterclockwise, which is S. Now, it's going to be the same for this. This is also going to be S. But now if we look at the blue current center over here, this is going to be priority group number one. This is priority group number two. This is priority group number three. And then the hydrogen here, be careful. It is on a wedge, right? So because of that right there, if you go rotate it this way, it looks like an S because it's going counterclockwise, but it's actually going to be an R because the hydrogen here is on the wedge. So we just invert it to whatever it looks like normally, right? So on the left side, the red color center is an S, the blue color center is an R. We already know that on the right side, the red color center is an S. Let's assign RS for this color center here, where this is one, this is two, this is three. We go this way, S, and it will stay as an S. We do not have to invert it because the lowest priority group here, hydrogen, is already on the backside, the dash. So it will stay as an S. Now, if you look here, the red color center stayed as an S. If you look at the blue color center, it inverted from an R to an S. So we see that some color centers invert, in this case, the blue color center. Some color centers stay the same, in this case, the red color center. So these two molecules here will be considered diastereomers from each other, right? Any questions on this diastereomers concept?
No, no, thanks.
That's good. Okay. So now the other thing that I want you to know about are meso molecules here. Okay. So meso molecules are going to be achiral, right? They're going to have two chiral centers, usually one R and the other one would be S. And the important thing here about mesomolecules is that they have a plane of symmetry. Right? So an example would be something like this. We see that there are two car centers, one here and another one here, right? And even though this entire molecule has two car centers, one here and one here, this molecule is considered achiral overall because of this plane of symmetry. Like through this plane right here, everything on this side is the same as everything on this side. They are symmetrical, right? And because of this plane of symmetry, this is going to be achiral, right? Specifically, this molecule is a mesomolecule because there's two car centers and a plane of symmetry like that. Now, it can get more tricky because if you have this structure over here, we do see two car centers, one here and another one here. And right now, as it's drawn, we do not see a plane of symmetry, right? Clearly. But we see that there is a single bond right here that can do free rotation. So when we do rotation like that, we're gonna get this molecule redrawn, where this is the red car center, this is the blue car center. And the reason why we inverted the dash bromine to the wedge bromine was because we want this molecule to be the same molecule as this molecule here. We just rotated this bond, right? But when we do that, we have to make sure that this blue car center stays the same RS configuration. So if you take a look at this car center here, this is priority group number one, this is priority group number two, this is priority group number three, and the hydrogen here that is a wedge is the lowest priority group, number four. So if we go one, two, three this way, that's going clockwise and it looks R, but it's not actually R because take a look at the lowest priority group hydrogen here. It's on the wedge, so we have to invert it to an S. So that is an S chiral center here on blue. We want to maintain the same S chiral center for this blue to make sure that this molecule is the same molecule as this here, right? Because we're rotating this single bond right here. So this is priority group number one, two, three. Going this way is counterclockwise, which is S, and we stay as S. We do not invert it to an R because the lowest priority group here is on a dash hydrogen. So that's good. We could keep it like that. Right. Okay. Nice. So now the reason why we redraw like this is because we now clearly see the plane of symmetry down this plane of the molecule here, where everything on this side of the molecule is the same as everything on this side of the molecule. They're symmetrical, right? And then making this molecule meso and therefore achiral, even though there are two car centers here, right? Any questions on this meso molecules concept here?
No, thanks. Thanks.
Yeah, that's good. That's good.
But I
Now,
think we stopped there at the university. That's
oh,
all the core we have.
like you went over this in your university already?
No, no, we don't commence it.
You guys don't go over meso molecules or enantiomers or diastereomers? Do you guys go over RS?
We stopped there.
We're still there, the RS configuration.
Yeah.
Okay, so do you want to do practice with that instead? RS? I could give you like practice problems on that, and then we could work through it together.
Someone.
hmm Yeah, let's do some similar problems to that. Okay. So, let's say we have this, let's start off with this right here. How many chiral centers do you see in this molecule here?
Two.
Yeah, two, correct. Um, one here and another one here. Let's look at the red chiral center. Is it R or is it S?
It's an S.
It's an S, okay. So let's see here. I'm gonna draw out the invisible hydrogen for you, which is in wedge. And let's say this is group A, this is group B, this is group C, this is
How
group
I
D.
find the invisible hydrogen?
Yeah. So the invisible hydrogen here is going to be on a carbon that is neutral, right? And you know how carbon is neutral with four bonds?
Yeah, four.
This carbon here, how many bonds do you see drawn out right now? How many bonds?
Three.
Three bonds, right? So we're missing one bond, right? That
Yeah,
missing one bond is invisible, and which is the invisible bond to hydrogen, which could be like here, it could be here, or it could be here. It does not matter because you know how when we do the direction, like clockwise is R, counterclockwise is S. The fourth group does not matter on what direction it is because the lowest priority group will always be on the backside, on the dash, right? But what do you notice about this hydrogen here on this carbon here? Like it is not on the backside, but it is on a wedge. So when you do it normally, what do you have to do at the end, right? Like this is number one, this is number two, this is number three, right? Um, were these the same priority groups that you chose right here?
that's an S.
Uh-huh. Yep. So this right here is going counterclockwise, which is looks like an S, but the lowest priority group here, hydrogen, is on the wedge, so it will not be an S. We flip it or invert it to an R because of this lowest priority group here on the wedge. On the wedge, we know it's wedge because we said earlier that a carbon can have two flat bonds, one wedge, and one dash, right? And if we look at this carbon center over here, this carbon here already has two flat bonds, one dash. So that means the missing bond here that we do not see is a wedge, right? And because the lowest priority of hydrogen is a wedge, we invert it to what it looks like, which is an R. Does that
Clear.
make sense?
Thanks.
Yep, that's
Clear,
good.
clear.
That's good. Now, can you do the same for this blue carbon center over here?
That's an S.
Okay, so let's see here.
Sure.
This is number one. This is number two. This is number three. Going this way is clockwise, which is an R, and we know that the hydrogen here has to be a dash hydrogen, right? Because this carbon here already has two flat bonds, one, two, and a wedge bond already. The wedge bond is already given to us as a methyl group, and because of that, the hydrogen here has to be a dash because a carbon can have two flat bonds, one wedge bond, and one dash, right? And because the hydrogen lowest priority group here is or the backside, we keep what it looks like, which is an R, which is an R. So this is an R right here. So both of these car centers here are R's. Any questions on that one? On this one?
I can place the hydrogen left of the three or right. No
Yeah,
problem.
yeah, no problem. You can place the hydrogen here, or you can place the hydrogen here, or you can even place the hydrogen up here. It will not matter because what matters here is the where is the one, two, three going to? One, two, three is always going to be clockwise.
Clear.
Yeah. Mm-hmm. Okay. Let's try another one here. Okay. Try this one here. There's two car centers, one here and another one here. Um, look at the red one, the left one. Is that R or is that
How
S?
I found the car centers always?
Yeah, the first step is to find the car centers always. How many there are, right? And we know that there are two in this case. Right.
How you
And
find the red one?
yeah, so the red one is a car center because there are four unique groups attached to it. There's this ester group, there's this ethyl group, there's this R group, this random group right here, and there's one more invisible group, which is the hydrogen here.
The car center is always a carbon who did the three liaison, and the fourth is not invisible.
The fourth does not have to be invisible. In this case, it is invisible, right? Kawasaki will always, always, always be a carbon with four different groups, four unique groups,
Mhm.
right? And in this red Kawasaki here, we see four different groups. We see an
Yeah.
ester, this group, and this group right here. But if you look at another example here where we have, let's say, like this example over here, this car center here also has four groups. This group, this group, this group, this group, but there are no invisible hydrogens on that carbon. There's no invisible hydrogens there, right?
Clear.
Right. This is also a car center, but there is an invisible hydrogen here because we only see three bonds. But this carbon here, we see four bonds, so there are zero hydrogens there. Okay, that's good. Okay, so now let's draw that hydrogen out in a dash, and it has to be a dash because this carbon here already has two flat bonds, one wedge bond. So the missing bond has to be dash like that. Given that right there, what is the RS configuration for this chiral center? Is it R or is it S?
That's an R.
An R, right? So let's check here. One, two, three,
Three, four.
clockwise, R, and it stays R because the lowest particle group, 4, is on the backside. So we keep it as an R. Nice, right? But when we do RS here, we only worry about the one, two, three in that direction right there. 4 just helps us keep track of if the lowest particle group is in the back or not. If it's not on the back, if it's on the wedge, then we have to invert or flip it. But in this case, we don't have to flip it because it's already on the back like that. Okay.
Okay.
Now, how about for the blue car center here? Is it R or is it S?
I think that's an R also.
An R as well. So, let's say here, this is 1, this is 2, this is 3, and going this way, looks like an S, but it's not an S. It's going to be an R. We invert it because the lowest particle group here, hydrogen, is on the wedge. So we do everything normally, which is going counterclockwise, which looks like an S, but it's not an S. It will be an R because the lowest priority group 4 is on the wedge. So we just invert it at the end like that. Nice. Okay. Yep. Any questions so far?
No, no, thanks.
That's good. That's good. Okay. Um, are there any other problems or questions that you want us to go over? Like we could try this one here. This one here is a trickier one. How would you assign RNS for this one? What's your priority group number 1, 2, 3, and 4 here?
I think the SH is one, the
Hmm.
bear is two,
Hmm.
the
Yeah.
ethyl is three,
Hmm.
the methyl is one.
4, 4. Right.
These four.
Right. Correct. So this will be 3, this will be 4, but be careful here. When we're assigning the priority, we look at the first atom, sulfur versus bromine. If we go back to the periodic table over here, right? Sulfur has 16, bromine has 35. Like S has atomic number of 16, Br, bromine, has a atomic number of 35. So bromine is the one that has a higher atomic number, which will make this bromine number one and this S number two, like that, right? Any questions on why that's the case?
No, thanks.
Mhm.
You are a good teacher.
That's good. Yeah, I'm glad you're understanding this lesson. Okay. Um, Now there is a big problem for this molecule here, right? The big problem here is that if you look at the lowest priority group, that's not a hydrogen. We're used to seeing hydrogens. In this case, it is not a hydrogen, right? It's a methyl group. So we see that this methyl group or the lowest priority group is on the flat plane of bond, which is not what we want. Where do we want the lowest priority group when we assign RS? Do we want it in a flat bond, in a wedge like this, or in a dash like this? Where do we want the lowest priority group for us to assign R and S?
And
Mhm. So it would be the dash. When we assign RS, we want the lowest priority group to be the dash always, right? We can rotate this single bond right here to rotate this methyl group on the dash. This dash bromine will go become a wedge. This wedge SH will become a flat bond. And when we do that and redraw the molecule, this is what we are gonna get, right? The bonds here will stay the same, but the groups attached to the bonds will be different, right? The flat bond will be now be the SH, the wedge will now be the Br, and this dash is now the methyl group, right? So when we do the same thing, 1, 2, 3, 4, right? Because bromine has an atomic number of 35, sulfur has an atomic number of 16, and then carbon has a atomic number of 6. This is also 6, but this carbon is attached to this carbon, so that's why that's just higher. If we go 1, 2, 3, that's going counterclockwise. That is going to be S, like that. Okay. Any questions on why we needed to rotate this to make the lowest priority group here on the backside?
no, no, thanks.
That's good. That's good. Okay.
No, no, please, please, can you repeat it?
Yeah.
The
So
last one.
oh, this last one over here, this one?
No, no,
Oh, this one?
yeah.
Yeah, this one. Yeah. So the most important thing here for RS configuration is that you have to make sure that your lowest priority group, right, in terms of atomic number, so you look at the periodic table for that, is on the back side, right? AKA the dash, which looks like this, right? If the lowest priority group, which I'm gonna abbreviate as LPG, right? Lowest priority group. If the lowest priority group is on the wedge, which is this bond right here, invert at the end, right? If you have an R, invert to S. If you have an S, invert to an R. Like flip it, the end. If the LPG, lowest priority group, is on a flat bond, like this, rotate the three groups, like any three groups, keeping one group still, so that the LPG, lowest priority group, is on the back, right? So for example, what we had earlier, we had this molecule with this chiral center, where we know that bromine has the priority group number 1 because it has the highest atomic number, and a sulfur is priority group number 2. This group is number 2, number 3, and then this group is number 4. Now, we see that the lowest priority group, LPG here, is on a flat bond. We do not want that. We want the lowest priority group, LPG, to be on the back, the dash. So to make that happen, we have to rotate these 3 groups right here, keeping this group still. It's gonna stay still, right? Because we're rotating the single bond right here, where I'm gonna rotate the methyl group, the lowest priority group, to go to where the dash bond is. That's gonna push the bromine that was a dash to become a wedge bond, and that's gonna push this SH group that was a wedge bond into this flat bond here where the methyl group was. Nothing touches this group right here. It stays still. Nothing happens there. So when I redraw that, right, I just copy and paste the bonds here. I'm not copy pasting the groups, right? We know that this group stays still, right? This methyl group that I pushed up here is now this dash group right there. And this bromine here that I pushed into the wedge is now onto the wedge right there. This SH now is now onto this flat bond. So we draw our SH out like that, right? Um, it's still the same molecule. We're just rotating that bond right there, where we know that this is priority group number 1, this is priority group number 2, this is priority group number 3, this is priority group number 4. So when we do rotation here, that is going counterclockwise, which is an S, and we stay as an S. We do not invert it because we see that the lowest priority group here, LPG, is on the back, the dash. So that's good, right? So that's why we have to rotate it. We only do this rotation thing when the LPG is on a flat bond like this originally. We would have to rotate it and draw this structure here, which is the same thing as this. It's just drawn differently, which allows us to assign R and S more accurately, like that. Okay. Did that make sense, Amit?
Yes, yes, thanks.
Mm-hmm. That's good. That's good. Okay.
Can you tell me what's the EZ? EZ.
Oh, easy. Yes. So for easy, um, let's say we have an alkene like this, and we have also an alkene like this. Okay. Let's focus on the top, this alkene here first. Okay. So an alkene is a carbon double bond carbon. There's 2 carbons in the alkene, right? The red carbon and the blue carbon. Okay. Now, ignore everything on the blue carbon and take a look at the 2 groups on the red carbon. What is the higher priority group in terms of atomic number? Would it be this group on the red carbon or this group on the red carbon? What's the higher priority group?
The first.
Yep, the first one. So I'm going to circle that one in red. Now, I'm going to ignore everything on the red carbon, and we're going to compare this group and this group here. What's the higher priority group on the blue carbon?
The beer.
Yep, the BR, right. So I'm going to circle that group right there. Now, take a look at the double bond right here. Make a big line through that in your head and look at the relationship between the 2 priority groups, right? We see that the red priority group is on the opposite side as that blue priority group right there, right? They're on opposite sides of the line. And if they're on opposite sides of the line, we call that an E alkene. Now, if we do the same thing as over here, where if we look at the alkene carbons, the red carbon and blue carbon, we already did this earlier. This is the highest priority group on the red carbon compared to this group, right? Because we're gonna ignore everything here. If we were to ignore everything here and compare these 2 groups, the BR has the higher priority group, so we circle that group. Make a big line in your head through that double bond, like the same direction as the double bond. Don't make the line through here. That's perpendicular, right? We don't want that. We want the line to be like parallel on the same direction as that double bond right there. And then we look at the relationship between the 2 priority groups, the red one and the blue one. They're on the same side of the line. They're on top of the line, right? And because they're on the same side of the line, we call this a Z alkene instead of an E alkene. An E alkene would be when the highest priority groups, one from each carbon, is on opposite sides of the line through the alkene. The Z alkene is when the two highest priority groups, one from each carbon, is on the same side of the line, like that.
That's so clear. Thanks.
Yeah, that's good. That's good. Now, let's end off this session with a practice problem here. Let's say we have something like this. Okay. And we have a red carbon and a blue carbon. Let's ignore everything on the blue side and look at the red side. What has the higher priority group?
The
Which group?
BR.
Yeah. So be careful here. The BR does have a higher atomic number than the S, but when we're looking at priority here, we're looking at the very first atom attached to the red star. The very first atom attached to this red star here is the carbon, the C. The BR
Mhm.
is not attached to that red carbon, right? That's just there to trick you, right? So be careful of that trick because on the exam, you might see that trick, right? But you're not comparing the BR with this S, you're comparing the carbon with the S,
Okay.
right? So because of that, this group would be the higher priority group here, right? Not this group, even though BR is here. BR is a higher atomic number than S, but it's not attached to the red star where this carbon here is. So we're comparing this S C to this S right there. Okay. Now let's ignore everything on the red side. What has the higher priority group on the blue carbon?
The second one.
Yes, the second one, which would be this one over here. Make a big line through the alkene like that. What is the relationship between these two priority groups?
It's E.
Yep, E, because they're on opposite sides of the line. Nice. Okay. I
Thank you
will,
so much.
of course, no worries. I will send you the notes to your email that you signed up this session with, and then the recording to that email for you as well for you to review as soon as I can.
Thank you.
Yep, of course. Good luck, Ahmed.
Thank you. Good night.
Good night. Good night.